Hello, my name is Wilson Dumpang alias William. My metric number is BK15110276.
And my name is Frydoreen Masmin. My metric number is BK15110087.
We are going to present and explain to you about the Runge Kutta method of the numerical method. First, let me introduce to you a little bit about the Runge Kutta methods. I will start off with the history of Runge Kutta method. The Runge Kutta method was developed by two German men, Karl Runge and Martin Kutta, in 1901. Karl Runge developed numerical methods for solving the differential equations that arose in his study of atomic spectra. These numerical methods are still used today. He used so much mathematics in his research that physicists thought he was a mathematician, and he did so much physics that mathematicians thought he was a physicist. Today, his name is associated with the Runge Kutta method to numerically solve differential equations. Kutta, another German applied mathematician, is also remembered for his contribution to the differential equations based Kutta-Joukowski theory of A-foil lift in aerodynamics. So, in the early days of Runge Kutta methods, the aim seemed to be to find the explicit methods of higher order. Later, the aim shifted to find methods that seemed to be optimal in terms of local truncation error and to find Boolean error estimators. With the emergence of stiff problems as an important application area, the attention moved to implicit methods. From learning about the history, we are able to know and identify the general function of the Runge Kutta method. The Runge Kutta method are basically a numerical methods for solving the differential equations and is said to produce a better result in fewer steps. J.C. Butcher stated that the idea of Runge was to base the approximate solution not on this unsymmetrical and relatively inaccurate Riemann rule, but on such improved formulas as the midpoint and trapezoidal rules. The requirement of evaluating the derivative at the midpoint or endpoint of a step not yet completed was achieved by first performing an Euler type of calculation to obtain a preliminary approximation to the solution at one of these points. Riemann rule is a certain kind of approximation of an integral by a finite sum. Therefore, how accurate is this method? The Runge Kutta methods achieve the accuracy of a Taylor series approach without requiring the calculation of higher derivatives. Zing and Chisholm said that each increase in the order of the method produces an increase in accuracy even though the extra work has been accounted for. Hence, a higher order such as 5th and 6th order methods can be more efficient than the 4th order method if a sufficiently accurate spatial discretization is used. Now, the application of Runge Kutta method. According to Bellot and Vermiglio, Runge Kutta method have many applications including the numerical solution of delayed differential equation and of integral differential equations and the implementation of waveform relaxation iterations. These are some of the applications that we are able to implement the Runge Kutta method.
We have an ordinary differential equation that relates how y changes as we change x, and that's a function of x and y. Say I know a value of y, then I can make a small step, and the step is xi plus 1 is equal to xi plus h. So, we make a small step in h and then calculate the new value of y that corresponds to the xi plus 1. The step size is the amount by which x is increased for each steps. And we have this term here that is a function of xi, yi, and the size of the steps. k1 is just a function evaluated the x and y. k2 is also the function evaluated, but now x plus half the step size and y plus half the step size multiplied by the function k1. k3 is also similar, except it is y times k2 here. And k4 is evaluated at x plus full size and y plus the full size multiplied by k3. And so, this gives us a better approximation than the Euler method, which just used a function at the previous point. So what we want to do next is apply this formula on a differential equation problem. Let's take a look on an example of a fourth-order Runge Kutta method. The question is, use Runge Kutta method of order 4 to solve the following using a step size of h equal to 0.1 for x less than or equal to 0 and x less than or equal to 1 for y0 equal to 1. The differential equation is dy over dx equal to 5x squared minus y over exponential x plus y. From the given condition, where y equal to 1 when x equal to 0, we can substitute the value to get k. We know that k1 equal to the formula fxi yi. Solving the differential equation, we obtain the value of negative 0.367 at 7944. Next, we solve for k2. Note that k2 equal to fxi plus 1 over 2h, yi plus 1 over 2h, which means that we have to find the value of x plus half the step size and also y plus half the step size, which in our case, step size h equal to 0.1. Solving it will result in k2 equal to negative 0.345 35749. For k3 equal to fxi plus 1 over 2h, yi plus 1 over 2 k2h. The step to find x is the same as in k2, but for y, we will have to find y plus half the value of k2 times the step size. Then, we obtain the value negative 0.345 44563. As for k4 equal to fxi plus h, yi plus k3h. To get the value of x, we add x with step size. Next, we find the value of y, which can be obtained by adding y with k3 times the step size. This leads to the value of negative 0.315 439325. We then take the four values and substitute them into the Runge Kutta fourth order formula, which is yi plus 1 equals to yi plus 1 over 6 times k1 plus 2k2 plus 2k3 plus k4 times h. Solving this will result in the value 0.965582789, which actually is our new y value. Using the new y value, we will start again to find the new value of k. Solving this by hand would be tedious. Therefore, we will be using computer to compute the value. The result is shown in the table below. This formula can also be modified as said by Was 1990. The modified formula results in better accuracy. It is done by adjusting the parameter A1, A2, and A3. But modifying this formula can be tedious, and often the result obtained is similar with the classical method. This is supported by Tan and Chen. They mention that although the higher order of Runge Kutta methods can increase the error accuracy, but it will need to pay the cost of calculation complexity. Therefore, the most mathematicians think that the fourth order Runge Kutta method is the most efficient method to solve numerical solution for initial value problem. To conclude the Runge Kutta method, we can say that these methods helps us to solve differential equations faster with fewer steps compared to other methods, and help us to save time by avoiding extra steps.
Finally, we would like to thank Dr. Yoong Hou Pin, our numerical method lecturer, for guiding and helping us on understanding the Runge Kutta method. That's all from us. Thank you.